So on the agenda, we actually have something that is slightly embarrassing. In the video for the cross product, I regrettably forgot to mention one important property of the cross product. So let me share my screen for that. Okay, so we have the following. Imagine you have the following task: find the area of the triangle spanned by two vectors. So the idea is that you have a vector and a vector, and this could be R and this could be S, and of course the drawing is not accurate, but that's not the point. And you wonder, okay, what is the area of the triangle that we get when we connect these two, and then we are interested in this. And using the cross product, this is actually very easy because we have the following property. The length of the cross product between R and S is the area of the parallelogram spanned by R and S. So if we take a look at that, what we get is, well, let's maybe take this one. So this is also R, and this is also S. And then we have this area, and this area is precisely the length of the cross product between R and S. So if we want to compute the area of the triangle, all what we need to do is we compute the area of the whole parallelogram and then divide the whole thing by 2 because, well, the triangle is just half of the parallelogram. Okay, let's give this a go for these two vectors. So we need to compute R cross S. This is ijk 0, 1, 1, 0, 1, 2, 2, 2. Then for the I component, we have 0, minus 2. For the J component, we have 2, minus 2. So this is 0. And for the K component, we have 2, minus 0. So this is 2. So this is in total the vector minus 2, 0, 2, which has length 4 plus 0 plus 4, so square root of 8, which is 2 times square root of 2. So the area of the whole parallelogram is 2 times square root of 2, and hence the area, was it green? I hope so. This is then half of that, so this is just square root of 2. And this is how you compute areas of triangles and parallelograms. Just use the two vectors that span the whole thing. So if you have got points, then of course you first need to build the connecting vectors. That's something we've done many, many times. And then you just compute the cross product, the length of the whole thing, and then you're done. Any questions for that? Okay, great. In that case, what I'd like to do with you today is mostly look at the equations of lines and planes in three-dimensional space, because this is a skill that is very, very important, that you can actually actively do these things, transform certain types into another, and so on. So I would like all of you to give this task a go for, let's say, 3 minutes, I hope will suffice. I want you to find two different equations for the line in three-dimensional space that passes through the point 1, 2, 3 and the point 1, 1, 1. Just give it a go. And maybe post as a comment if you think you got something, just so I know if, yeah, time's enough. Okay, talk to me. What's your status? Is this easy? Is this hard? Are you lost? Do you have many different results? What's going on? And you can also just unmute yourself and talk to me. You didn't what? Okay, I think this just means we're going to solve this one together. You got an answer, but you're still trying. Okay, just to save some time, let's just solve this, or let me solve it for you. The general idea is actually easy. So for 2 points, finding a line between them is surprisingly simple. When you have 2 points, could be these two. Let's call this one P and this one Q. What do we need to describe a line? Well, to describe a line, we need something like a starting point. This could be P, it could also be Q, and it could be any other line, any other point on the line. And we need a direction vector, and then in this direction, we go for as long as we want. So for example, we can take, well, it should be a bit straighter. We can take, this is our direction vector, but we can also, use various different ones. We could use this one, we could use this one. And all of these kind of information we can combine to build a line out of these data. So for example, the easiest direction vector for our line is, of course, the connecting vector from P to Q, which is 1, 1, 1, minus 1, 2, 3, which is 0, minus 1, minus 2. So if we start at P and add 0, minus 1, minus 2, this is if we start here and then walk. Let's take this. This is PQ. And so if we start here and then add PQ, then of course we arrive at Q. But if we want to arrive, for example, over here, then we would add half of our direction vector. And if we wanted to go here, we would add it twice. And if we wanted to get here, we would subtract it. So if we want to describe the whole line running through the whole thing, we just add multiples of t of our direction vectors where t ranges from minus infinity to infinity. And we can call this r of t, and I think we call this the vector form of a line equation. But there's also, of course, different way of doing this. For example, we could also say, okay, we don't change the direction, but this time we start at Q. So we take the vector 1, 1, 1, and add multiples of our same direction vector. So this would mean we start here, and for t equal 1, we would then end up here, and for t equals minus 1, we would then end up at P. Different ways of doing that. For example, we can also multiply our direction vectors just by multiples of it. So instead of this, we could also use the direction vector 0, 2, 4, which is the minus 2 times the whole direction vector, which of course changes the direction vector. So this time we wouldn't go this way, but we would go something like this way. But the line itself, it doesn't change. We can also then reformulate these two things. So the parameter form for R1, this is then x is 1, y is 2 minus t, z equals 3 minus 2t, right? We have 1 in the first component, but we don't add any t, so we just get 1. In the second component, it is 2 plus minus 1 times t, so we get this one. And the third one, we start at 3 plus minus 2 times t, so minus 2t. The parameter form for R2 is, again, x is just equal to 1, y is now 1 minus 1t, and z is equal to 1 minus 2t. And of course, we can also reformulate this in the, what do we call it? The symmetric forms. So if you wanted to do like a parameter phi equation, in this case, it would be, well, x is equal to 1. And then we know that y minus 2 is the same thing as z minus 3 over 2. And so we get many different ways of expressing the same line running through these 2 points. Do you have any questions to that? And you can either post them as a comment or unmute yourself and talk to me. Can you repeat the last thing? Do you mean how I ended up with these ones? Okay. So if we have an equation like this, this always has a parameter, and maybe we think that a parameter is a bit of an annoying thing to do. But we know that, of course, when we plug in a parameter, we use the same t here and here for the same point. So what we can do is we can reformulate this equation as saying that, well, if y equals 2 minus t and z equals 3 minus 2t, and the t is the same thing in both cases, then, well, for the first one, we get that, well, minus t is y minus 2. And for this one, we get that z minus 3 divided by 2 is minus t. And so because these terms are the same, we can also express like this. We can't do anything with the 1 because in the 1 we don't walk in any direction. So we just copy x equals to 1. And we know now that this one has to be equal to this one. And that expresses the same line. Does that make it clear? Okay, perfect. Okay. So this is the way, or these are ways how we approach finding lines through points. Finding lines is very, very easy. A bit more complicated is finding planes, especially when you've got them set as multiple points. But there is a very, very easy way to find equations for planes if we want them to be perpendicular to something. So what we want to find now is we want to find a plane which is perpendicular, orthogonal to the this above line. So the line passing through 1, 2, 3, and 1, 1, 1. And we also want it to pass through the point 1, 2, 3. So our point Q. And again, I'll give you, let's say, 3 minutes to find an equation for this. Okay, how is everyone doing? Do you feel lost? Do you feel like you need more time? What's your status? Okay, you'll get a bit more time. So how is everyone else doing? I mean, there's, what is it, 29 people in this meeting, and so far only 2 of you have been interacting with me. How's everyone else doing? Yes, of course, I'll solve it in a bit. But I'd like to hear from other people first how they are doing with a question. Anyone? Still working on it. Okay. Well, to save some time, I guess I hope that you know what you're working on. Now you can check if this is basically what you're doing. So the idea is that we describe a plane mostly by using a normal vector. So we have a plane in space. And we try to describe it by using a vector n, which is perpendicular on the whole plane. Now, the task is find a plane perpendicular to above line. So, and above line already had a direction vector, and we can choose many different ones, but let's choose this one. Or actually, let's use minus this one, because then we don't have too many minus signs. So let's use 0, 1, 2 as a normal vector. So the difference in this case might just be that n is not pointing up but down, or whatever angle you're looking at. But of course, for building the dot product, taking minus of something only gives us a minus sign, and we're looking for perpendicular. So we're looking for a dot product that equals to 0, and that doesn't change anything. Now this only gives us a plane which is perpendicular to above line, but we still need to take care that it passes through this point. So imagine that this point right here, that this is our point 1, 2, 3. What we now have is that if we have another point, plane, any other point, let's take blue maybe, and we take the connecting vector here, then we get a right angle with our n. And this is now a general point on the plane. So we get a, now this here should be round. So what we get is the following. We have a general point on our plane, and it's characterized by the fact that the connecting vector to 1, 2, 3, so minus 1, 2, 3, is orthogonal to n. So dot 0, 1, 2 equals 0. And this is now the equation as we write it down, but we of course can simplify it. by just basically multiplying the whole thing out. So if we multiply the whole thing out, what we get is, well, we first build the dot product between our normal vector and our general vector. So this is just, well, 0x plus 1y plus 2z. And now minus the dot product of this guy with this guy. So this is 0 times 1 is 0. 1 times 2 is 2. Plus 6 is 8. And we can again simplify this to y plus 2z equal to 8, which is now an equation for our plane. And of course, we had different choices. I mean, we could have also used 2 times our normal vector here, because lengthening the normal vector, of course, doesn't make any difference. Or we could have taken an inverse or any other thing. And of course, we also could have chosen just a different point on the plane that we already knew was there, but that is a bit more difficult if you only know that this point is on the plane. Is this so far clear? Is this pretty much what you did, or is this very different from what you did?
Victor, can you get back to the answer at the end?
Oh, yes, of course. Sorry.
Yes, that's pretty much what I got, but different method, just a little bit different.
That is fine. I mean, there are, of course, different ways of approaching the whole thing. This, I think, is probably the quickest one, or at least the one that I find most convenient, or I find easiest to remember. But when it comes to finding equations for things, there are always many, many different ways of arriving at an answer. And of course, it's not quite clear that you would actually get this precise answer. So for example, if we actually had used this factor 2 over here, then what we would have gotten is the equation 2y plus 4z equal to 16, which is a different equation. Of course, this is just 2 times this equation. But in that sense, the answer isn't necessarily unique that you get. Okay.
Yes, but Doctor, I have just one question. Why did you take? Why did you change the sign of the vector? You changed -1 to 1.
Yes. Pure convenience. So when you start calculating things, you always want to reduce the potential sources of errors that you can then make with calculations. Okay. And one very obvious potential source of calculations is when you have lots of taking track of signs. So then you would maybe, if you had a minus sign here and a minus sign here and a minus sign here, then it's okay. This is now minus, minus, minus is still a minus. And so getting everything to as many positive signs as possible for me just reduces the errors in calculations. But there's no, of course, we could have used also -1 times the whole thing. And in that case, the equation that we would have gotten is -y minus 2z equals to -8. But this is just to reduce potential errors while doing the calculations.
Okay.
Okay. Then I think we're ready for the last task of the day. Okay, now we have this plane perpendicular to above line and passing through this point with any one of these equations over here. And now I want you to find the distance between this above plane and the point -1 to -3. And again, you get something like 3 minutes for that. Go ahead. Damn it. I think now the screen share stopped. Okay, how do you feel about this exercise?
Doctor, I tried it, but I don't know. I got 0. Maybe it's not correct.
I actually don't know. We're going to check that in a minute because I just made up this point and haven't calculated the actual distance yet. But let's give it a go. You had a formula. Okay, well, maybe just on the plane, that it would be totally fine. I mean, we can actually just check that. Is so y. This is our y coordinate. This is 2 plus 2 times z. This is -6, so we get -4. So this is definitely not equal to 8. So we can't get a result of 0. Because this plane, this point is not on our plane. But let's see what the issue was. So we had the following formula for the distance, which was you take the absolute length of a x1 plus b y1 plus c z1 plus d, and then you divide it by a square, b square, c square, and then the square root out of that. Now, we need to check which, or we need to now remember, okay, what is x1, y1, z1, what is a, b, and c, and d? So in our case, this is x1, this is y1, and this here is z1. And what are our a, b, c, and d? Well, we get our a, b, c, and d from this equation. We just need to bring it all onto the left-hand side. So if we bring it all onto the, okay, actually we already brought it onto our left-hand side in this formula. Let's put it, yeah, okay, let's put it here, I guess. This is our A, this is B, this is C, and this is D. So let's plug it all in. Then we see that on the top, we have 0 times something is 0, then we have 1 times 2 is 2, then we have 2 times -3 is -6, and then we add D, which is -8. And then we divide the whole thing by a square plus b square plus c square. So this is 0 square plus 1 square plus 4 square. So this is -4 minus 8 is -12. So this is 12 over square root of wait, this shouldn't be 4 square. Sorry, it's a 2 square, which is 4. So we get square root of 5. And that's the distance then. Do you know where the problem lay when you tried to calculate the distance between the plane and the point?
I probably didn't pay attention to the point that was given at the last question.
Okay. But is this clear how you calculate the distance between a plane and a point, given already a plane in normal form? Okay. Then I think from my side, this is it for today. Do you have any questions about, well, topics concerning these or these kind of topics? Anything you'd like to ask? Test 1. I'll decide. So still figuring that out. Date for test 1 will be published, I hope, tomorrow. So the date will be published, not the test will be tomorrow, of course. Anything else? Okay, if that doesn't seem to be the case, so I wish you a great start into the week and see you again on Thursday, hopefully. Have a great week until then. Goodbye.